Title of the talk is Thorium dioxide for light water reactor applications, and I will give you some historic background and tell you something about the ongoing research at SEK. Thorium, well, it is in the media. Alternative nuclear energy, the biggest invention since fire. Thorium, nuclear energy without waste. Whoa! Asia is working on the energy wonder of thorium. Oh, thorium put to test as policymakers rethink nuclear. Thorium, whoa, even an alternative for windmills. Is it really a miracle solution? And if it is, did thorium really remain overlooked for decades? Were we so stupid? Well, let's go back into time. And we're in 1953. What happened in 1953? Well, that was the first successful ascent of the Mount Everest. Edmund Hillary and his Tenzing were successful that year. Same year, President Eisenhower launched officially the Atoms for Peace program, which was the official start of building the shipping port nuclear power plant. Let's go a bit further, 1957. What happened in 1957 was the launching of the first satellite, outer space, Sputnik, USSR. And at the same time, 4 years after the decision to build a nuclear power plant, it was the first criticality of that nuclear power plant shipping port that for its first core was running at 60 megawatt thermal and was using uranium, zirconium, metal fuel, and uranium dioxide blanket. 1958, a very famous year, was the first opening of a Pizza Hut. We had the World Expo in Brussels, and here inside SEK, together with Belgo Nucleaire, we started the plutonium laboratories in the chemistry building. All this as a prelude to the 1960s. You notice that I didn't speak about thorium yet. 1960s, well, in 1960 itself, the feasibility on the thorium uranium-233 light water reactor breeder cycle was started. It was noted by the physicists that you could take advantage of the fertile isotope thorium, not fissile in a thermal spectrum, could lead through neutron absorption and then decay to a fissionable isotope uranium-233. Well, the same decade, 1963, SEK and Belgo Nucleaire, again, first in the world was the loading of MOX fuel rods in the BR3 reactor, and that same decade, a lot of other mixed oxide, uranium-plutonium mixed oxide programs in the fast reactor context was performed in the BR2 reactor, along with other reactor experiments in the Dounreay fast reactor, in Rhapsody, and in Phoenix. 1965, USA, shipping port reactor was starting with its second core, 100 megawatt thermal, uranium dioxide, high-enriched uranium, and the natural uranium blanket, still not going for the thorium, but that same year, the light water reactor breeder program started. And that was a huge program meant to deliver proof of principle of the thorium uranium-233 cycle. And it was a program that ran for around 12 years, and that ended with the decision in 1977 to load the shipping port third core that consisted of a seed thorium uranium-233 and a thorium dioxide blanket, and that was launched by President Jimmy Carter. Shipping port third core ran for 5 years successfully between 1977 and 1982. Well, thorium, an alternative for uranium? Well, we've seen that it has been studied for more than 50 years already as alternative to the uranium-based fuel cycle. Why so? Well, thorium is understood to be, the reserves of it are understood to be substantially larger and better distributed than those of uranium. And that is based on general models of the Earth's crust. Uranium reserves with huge deposits in USA, Canada, Australia, Kazakhstan. When we look at the thorium reassured reserves, they are differently distributed with huge reserves in Brazil, in Turkey, and India. So, although the general models state that there should be more thorium than uranium, the fact that uranium reserves for commercial reasons are much better mapped than the thorium reserves, the identified resources of uranium are today larger as those of thorium. But some countries, for example India, have indeed much larger thorium reserves than uranium reserves. Well, and natural thorium is not fissionable but in a thermal neutron spectrum, but acts as a fertile isotope for uranium-233 through the chain that I indicated before already. So, thorium-232, 1 neutron, thorium-233, stable, half-life of 22 minutes, beta decay to protactinium-233, half-life of 27 days, beta decay to a fissionable uranium-233. Well, some facts about thorium-based fuels. It has acceptable neutronics and physics behavior. Has a reduced breeding of long-living minor actinides. Breeding is possible in both a thermal and an epithermal spectrum. Disadvantage is that it needs a seed fissile isotope because it's not fissionable on its own, so it needs to be lightened by uranium-235, plutonium-239, or plutonium-41. There's a smaller delayed neutron fraction in uranium-233 as compared to uranium-235 fission. Fission is there. Means that you have a more nervous reactor. The fact that you have a relatively long decay time of the intermediate protactinium-233 as compared to the comparable intermediate isotope in the uranium-plutonium chain means that there is a reactivity increase after shutdown, which is different in the thorium-uranium cycle than in the uranium-plutonium cycle. And it has the production of uranium-232, which is the top isotope of a chain which contains very hard gamma emitters. Can be a pro, can be a con. That depends a bit on how you see it. For proliferation-related issues, it's good to have to be able to trace wherever your uranium-233 is by the fact that it has a little bit of uranium-232 with it. On the other hand, for fuel manufacturing, a hard gamma emitter makes life much more difficult. Reactor feedback exists for various reactor types, high temperature reactor, heavy water reactor, pressurized water reactors, molten salt reactors, and most of the feedback exists for thorium uranium-235, a bit lesser for thorium uranium-233, and almost non-existent for thorium plutonium. So, why would one want to embark on thorium? Well, resource concerns have initially led to the early developments for breeding concepts, both for uranium in the fast reactor system and for thorium in the high temperature and molten salt fuel cycles. Geopolitical concerns have been the incentive for some countries to develop really a thorium cycle. Mainly today it's India. Long-lived waste concerns have been the driving force behind mainly European incentives for the revival of the thorium fuel cycle. That indeed generates less long-living minor actinides. And excess stockpile reduction of military-grade plutonium has been envisaged. Well, deterrence, I noted it already. Thorium-uranium fuel needs a seed fissile material. Can be uranium-235 or plutonium-239. Thorium-uranium-233 fuel manufacturing needs remote operation, and the thorium-uranium-233 breeding is only feasible in optimized breeding conditions. The fuel also has a reduced Voigt coefficient and shutdown margins, so quite some concerns for optimization and design of the power reactor in which it is to be run. Well, this is somehow to set the scene. I would now like to switch to what SEK contributed in the thorium-plutonium. Well, let's go back to 1999. Noted that the any thorium-based fuel cycle that would be implemented in the current fleet of reactors needs to go through a uranium or a plutonium phase. SEK stood already at the cradle of the MOX back in the early 1960s and continued to do so together with Belco Nucleaire for licensing of MOX fuel both in light water and fast reactor systems. So in 1999, we decided to embark on a thorium-plutonium study for light water reactor applications. And that was together with Transuranium Institute, and since then thorium dioxide fuels have continuously been studied at SEK, fabrication, in-reactor performance, safety studies, spent fuel behavior, post-irradiation examinations. That was mainly done in a European context. Europe had strong, in the past, in the 5th and the 6th framework program, several thorium-based initiatives, mainly in the context to reduce the nuclear waste burden. And there was, in the 5th framework program, there were 3 projects: the thorium cycle, OMICO, and Red Impact. OMICO was coordinated by SEK. In the 6th framework program, it was the LWR deputy program, also coordinated by SEK. These programs consisted of design of fuel, fabrication, irradiation rig development, because we were using the BR2 reactor, irradiation, post-irradiation examinations, and interpretation. All along the line was co-development necessary. The OMICO program ran between 2001 and 2007. It contained the design, fabrication, instrumented irradiation to relatively limited burnup, and co-development. LWR Deputy 2006-2011, PIE, radiochemical analysis and reference data sets, core assessments were performed. And TOMOX 2012-2015 in irradiation to industry relevant burnup levels and further co-development. Let's have a look at OMICO. Well, these are the guys from the Transuranium Institute working with a large team on a single fuel rod. And here you see a detail about that fuel rod, and here is the welding of the end plug. Work done at SEK, well, assembly of the irradiation rig. This is the irradiation rig, and here are the nuclear fuels. So this is an enlargement, bottom side. Those are 8 rods of 25 centimeter height each, instrumented on both ends, and the entire thing here is hanging in the technology hall. And here we have a view, top view of the BR2 cover. Well, that's what came out of that experiment. That's as a function of time in hours. We have a recording here are the experimental values, recording of the centerline temperature, around 1200 degrees centigrade, decaying a little bit with time because the power was reduced a little bit in the rods. And those were the calculations of that centerline temperature. These were the model predictions, model calculations in 2007. We have here, well, we were kind of mixed feelings. At least the measurements were bound by the calculations with a 400 degrees centigrade gap between the two. This wasn't too hard to get, I would say. So a little bit mixed feelings. That's why LWR deputy program succeeded in this one, where post-irradiation examinations were needed to refine the input of the codes, as well as thermal conductivity measurements and model developments. This was where these data were acquired for an irradiated fuel, then modeled, and then also a transition for what would this give for under irradiation was performed in the period that LWR deputy was running. ThO2 programs followed, well, is now still ongoing, in fact, 2012-2015, while the same rods continued their irradiation. This was in the period of the OMICO program, this is in the ThO2 program, and the essential part of it is that we reach now close to 40 gigawatt-day per ton, which is industrial relevant burn-up for the fuel. During that time, the post-irradiation examinations continued to be performed in order to feed additional data for the code developers. And today we can say that experimental values are the same. We are now capable of doing relatively good calculations, thanks to the work performed over the last 5, 6, 7 years. So we were happy. Where do we stand today? Well, performance qualification of thorium plutonium dioxide has been achieved with this 40 gigawatt-day per ton. So in a technology readiness level scheme, we are somewhere at level 3, qualification. In the more detailed scheme, that goes from 1 to 9, 9 being actually proven and operating in a power reactor and so on. We're still, well, this arrow, there is still some path to go. What should we do in order to go from qualification to demonstration level? Well, elaborating production routes that can be implemented on an industrial scale with less than 4 people on a single fuel rod, for example, is really necessary. Demonstrating the in-reactor performance in a power plant is the next step, and further quantifying back-end solutions. When looking at the papers that appear and the news that is being published in the general journals on thorium, interest is indeed rapidly growing, and SEK continues its R&D by implementing a new fuel synthesis laboratory in which thorium research is being performed, several PhD master thesis works, and a collaboration with the industry on valorization of thorium stockpiles. Oops. Yeah. Fuel lab established in the chemistry building, here we have a view, was one of the achievements over the last years, thanks to co-investments of the nuclear industry. Solid state research. PhD thesis on urania and thorium-doped fuel between 2011 and 2015. Advanced manufacturing routes, master thesis of Maciek in 2013-2014. Synthesis of thorium-doped with gadolinium via wet routes. Peter Sapka, 2014-2015, master thesis. Recycling of thorium, internship earlier this year, and a master thesis of Lucas. Lucas, is he here around this year? And improving the sintering behavior of thorium. Thaddeus, He just started. It's over there. Angela, where is she? Oh, over there, yeah. So several master theses and PhD theses are being conducted on that thoria fabrication route. With quite some success, I would say. Solid-state synthesis without pre-milling. You see the heterogeneity in the picture. On after pre-milling, you have already quite a much better microstructure, and with a suspension coating process, almost ideal structure is obtained. In manufacturing, also the powder production route is to be studied, and several, these are studies performed inside SEK standard route, homogeneous precipitation route, deliver different sizes of powders. The goal being to have both well sinterable, hence very fine powder, and free-flowing, hence being able to roll. Well, this one is well sinterable but not free-flowing. This one is free-flowing but not sinterable. So the next step is to combine these two into something that is and free-flowing, and free-flowing means that that you can transport it through a tube without too much effort, and sintering means that you can make a pellet out of it. So this was work done in the context of master thesis last year, and we will continue on this work in the coming 4 years. Well, an outlook. Where do we stand today with our thoria experience and with the interest and what is still to do? Well, there is today a global interest in fundamental and applied solid-state research on thoria-based fuels, and that continues only to grow. If you look at the number of papers being published every month, there is a steady growth in that. Thorium-uranium fuel as cycle in optimized reactors, the dream of the 1950s, 1960s, that still remains a very long-term option. But thorium-plutonium fuel could become a possible alternative for conventional uranium-plutonium MOX fuel in the current PWRs, if one wishes to go so within the next 15 to 20 years. Could be a reason to evaluate existing thoria stockpiles, reduce the existing plutonium stockpiles, reduce the minor actinide content of spent fuel. If we look at what we have obtained so far, then it's obvious that there are a few steps to take still. And one of the most important ones is that the elaboration of production routes that really can be implemented industrially. Efforts on thoria feed powder and the fabrication process itself must be thoroughly worked out. Blending, powder processes, pellet fabrication, scrap recycling routes, etc. Demonstrating in-reactor performance in a power plant and performing all the safety studies that precede such a demonstration is also a second route to go. And then a third route, fuel back-end solutions that need to be further quantified. Stability of thorium-plutonium under geological disposal conditions seems to be superior than that of regular MOX. If one would go for reprocessing, well, reprocessing of thorium-plutonium certainly is a huge challenge chemically. Well, my message is that it is not a miracle solution, but surely is a viable option. And thorium got its name after the god of war, the god of thunder, Thor. So maybe one day this thorium could serve to give us light. Thank you.